Right, unit standard 18239, element 4, and series circuit, first of the three circuits that we have to analyse and measure in detail. So I've drawn up a circuit here, made one up. We've got some actual resistor values, because we're going to have to build and measure this later, but firstly we have to do some analysis. Now the first thing you're going to be asked is to find the total resistance. Now that's not too tricky at all, they are in series. What we're actually asking is what, if I just go around, imagine that's one big resistor. What resistance is this battery, the 9-volt battery, seeing here and here? Or if you put a multimeter here and here with the 9-volt battery unplugged, what resistance would you would the multimeter say you have? Now, and it is very simple. Our total resistance for series equals R1 plus R2 plus R3, which of course equals, in this case, 330 plus 22 plus 470. You probably should be able to do this in your head, but I'll go quick here and I don't want to make any mistakes. So I'm going to whack that through. 470 equals 822, and don't forget your unit, 822 ohms. Okay, right, so we've got that, and there's part A done. Part B, as it will be on your schedule, is we want to know, the next thing is the total current. They ask in a nice order here, the questions, the things that you'd be expected to find out. So the current, now by the way it says IT, in fact it should say I, because some circuits, there are different currents throughout, but this is just a single circuit, single loop, therefore it only has one current. It's the same current here as here as here as here throughout, okay, because there are no nodes, there are no intersections. Different currents is where you've got something down here and you've got an intersection and things go off here and then there's something here, etc, etc. That's where you'll have different currents between here, here and here, but it's not the case here. We have one loop, one circuit, therefore we have one current. To find the current, well, firstly I should have set ourselves up, we use a fair bit of Ohm's law here, so I'm going to sneak the triangle for Ohm's law in here. If you'd rather just write V equals I times R somewhere, that's fine, but if you want to do the triangle version, V, I, R. There we go. Right, carrying on. So I equals, put our hand over I, and we get I equals V over R. V over R, which equals, now this is for the whole circuit, so the total voltage is 9 volts, and the total resistance is 822. Okay, so we should be able to calculate that. I'm just going to go 9 divided by the answer to the previous problem, and we've got now a number here which is pretty small, less than 1. Now it's best if you can get that number. If your number here says something like 10.9 blah blah blah, and then has times, and then has an e or something times 10 to the -3 here, that's going to be a reading in milliamps or something else. It could have a -4, could have a -2. So I think probably to keep it nice and safe, you want it where there's no exponent thing at the end of it. Come and see me to get your calculator sorted for that. It's best to have it just in the most plain form so that you don't get confused. If you know that you can handle that and you won't get confused and you'll do the right things, and then great, you go with it. But otherwise, I think it's best to try and get it in that form, just in amps, not milliamps, in amps. I'm going to get to 3 significant figures here. 109. We round the 4 down. There we go. So now unit amps. Okay. If you get a milliamp answer, then you're going to have to do some other things with the next calculation. Try and get it in amps if you can. Just make that point a bit clearer. Moving on. Now the next thing you'll be asked, VR1, the voltage across R1 from here to here. Okay, now once again we go back to Ohm's law. V equals I times R. Now not just which R? RT, the total? No, R1. Okay, because voltage across R1, we want to use the resistance of our R1 here, so which equals, okay, I is 0.0, it pays to get the previous answer right, otherwise you're in trouble. Times R1 is 330, which, well, we can keep going out to the right here, which equals, and we've already got that number in there, times 330 equals, okay, it says 3.61. We'll make it 3.61, at least 3 significant figures when you do your answers, please, otherwise you're going to get a whole lot of rounding errors as you go through. Unit volts, okay, that's the voltage we're doing. VR2 equals I times R2, which equals, and now we well, we'll have to start again from scratch here. 109 times what do we got? 22. Okay, I better just put 0109 times 22, which equals 0.240 if we round that, isn't it? Volts. Excuse that 4 there. Alright, does that make sense? We've got a much bigger resistor here, over 10 times bigger, this resistor, than this one here. We actually expect a voltage across it to be more than 10 times bigger, well and truly more than 10 times bigger, which indeed it is. Okay, little voltage across a little resistor. Sorry for the light fading in and out. Hey, look at that. Whoa, whoa, dude. Okay, that's crazy, isn't it? Alright, moving on. VR3 equals I times 3, and again, this is now just getting too easy. 470, which equals, we'll just whack that out for you, 470 equals 5.12, and again, look at it and say, does that make sense? This resistor here is bigger than this one, maybe another 50% roughly bigger than this one, and indeed it is somewhat bigger than this one here. Volts. The last thing to actually check that you've got that right, I would suggest, is let's actually do a bit of addition here. You see, we know that the sum of all the voltages around a loop should equal the power supply voltage. So actually let's add these voltages together and see what we get. So let's do that here. 5.12 plus 0.24 plus 3.61 equals, look at that. Now of course there's rounding error, but you round that up and you've basically got 8.97 to 3 significant figures. That is 9 volts, okay, as you would expect, roughly equal to 9 volts. One more thing is asked of you, and this is the tricky one that people often mess up on. Here, I'll try and get everything else for you to view so far, and I'm just going to add to it. You will be asked the power across, let's make it the power across R1. It could be the power across this, R2, R3, just check when you do it, but I'm going to do the power dissipated. That's the power transferred from electrical energy to heat energy in R1. Okay, equals, and you just expected to know what to do here. So, firstly, we need a formula for power. P is equal to V times I. You need to remember that. People will often get everything else right and then they'll mess up this question here. You have to get it. It's compulsory to get right this question on power. It's one of the individual PCs of this test. So, which equals, now, I'll tell you what people often do wrong. They'll go V times I, great, which equals, and they'll put in, now what they'll do now is they'll go 9 times the current 0.0109, which equals whatever it equals. That is wrong. Why? That is wrong. The 9, it's not 9 because we're not looking at the whole, this here would be the correct equation for the voltage across the whole power, dissipated by the whole circuit, but we're wanting the power dissipated by just this resistor here, R1. So let's actually flick down and have another crack here. P equals R1 equals, so that's a mess, V times I, which equals V R1, that is, times I. There's only one I. okay, which equals 3.61 from here. Oh, we're still fading in and out, aren't we? Crazy. Times, what do we got? 0.0109 amps, which equals, let's quickly plug that in, we're nearly done, 3.61 times 0. I didn't need to put 0, did I? Anyway, what a waste of time. Equals, okay, and that is 0.039. We'll do 3 significant figures. One might argue that we've only got 2 significant figures up there, so we should only have 2, but anyway, whatever. Oh, you can't see it. There we go. There's our answer there. And unit, watts. Okay, you must get the unit there as well of watts. Okay, other than that, we are, and by the way, in the assessment and practice assessments, we might get a much lower value of that. We might have a whole heck of a lot of zeros before we get to a number, and that's all fine. Very small amount of, for example, if we'd done the 22 ohms here, that would be a really small amount of, you'd expect at least one more zero there. Okay, so that's to be expected. Okay, all done.